video we're going to be going through the basics of binomial expansion. So I'm going to go ahead and start by kind of pointing out what we mean by binomial expansion. When we talk about a binomial, this is anything with two terms. We can say roughly it's like some a plus or minus some b value here. What we want to do is expand this, but by expand we mean take it to some positive n power where n is some integer. And I think I want to point this out here. But basically, if we were to say, a plus b to the first, or a plus b to the second, or a plus b to the third, what do you get when you expand these? And what you find out is, a plus b to the first, of course, is, I'm just going to write a plus b. I'm going to put a box around it. But there are patterns that show up here. And basically, the whole point of this video is to kind of outline how this binomial theorem works so that we can do it in general. But to indicate what the patterns are when you expand these things to some power, take a binomial to a power. So taking it to the first, we got the same expression. If we raise to the second, remember that these two things right here are not equal. What we need to do is we need to actually write this out. So these right here would be written out thusly. We'd say, well, we get a times a, which is a squared, plus, ab plus ab. So we get plus ab plus ab. I'll write that out there. We say plus now b squared. So combining like terms, we end up with this here. I'm going to take a different color here. We say 2ab in the middle plus b squared. And this is our final expression here, and this was our final expression over here. Now, when we raise this to the third, what I'm going to do is I'm actually going to point out the fact that we can just call this, a plus b, and then we could just say that this is times a plus b squared. And the only reason I say that is because we just found a plus b squared to be this. So it's really a plus b, and you can see how we'd have to take this times a squared plus 2ab plus b squared. And already, not that I have much of an issue with this, I mean, I would get a times a squared as a cubed. A times 2ab would be plus 2a squared b right there. And then a squared times, or a times b squared would just be plus ab squared. And then furthermore, we'd say, b a squared, or we could call it a squared b. We could say that b times this would be plus 2ab squared, and then b times b squared would be b cubed. So combining like terms, which is, just super fabulous thing to have to do here, we could say that we get a cubed plus, now I've accounted for this, I say a squared b here, a squared b here. So we say, well, two of these plus one more of those would give me 3a squared b. And then we'd say plus, now I've accounted for those, we say ab squared. We got one of them here and two of them here, so we get 3ab squared. And then last but not least, we'd say I've just got a b cubed. So I'm really going to try to say, well, I hope you can notice this here, because the patterns that show up vary here, but one that is constant is this. When we took a plus b to the first power, that is, what we want to do is kind of explore what we get when we take it to the nth power. But when n, we'll call this n, when n was equal to 1, we got a to the first, b to the first. And when n was equal to 2, here's what happened. I got a squared plus a to the first, b to the first, plus, sorry, I'll look at the last expression here. A squared plus a to the first, b to the first, plus b squared. And then on this last one here, we raised a plus b to the third. So we say n would be equal to 3. Essentially here, we started with a having all of the n here, a cubed. And as you go across, I'm not looking at the coefficients here. I'm not looking at those. But look at the variable values. We say a cubed, but then it's only a to the second power, but then b to the first. And then we say then it's only a to the first power, but then b to the second. B got one bigger. And then we say now here, there would be no a's left, a to the 0. Or we could write 1 times b cubed. So when we expand things to a certain power, we'll end with this today. We say what is x plus 4. Let's do this. We say a plus b. Let's do a plus b. Excuse me, a plus b to the fourth. What we're basically saying is this. When you do binomial expansions, the first thing we want to comment on is the fact that we have two quantities on the inside of this here. And these two quantities are some first value and some second value. Okay, so these two quantities here are a and b. And when we expanded these, this n value played a large part in this because in every expansion we say n is 1. We said a started with all of the n. And we said it's a constant trade-off of power as we go from left to right in this expression. So then b ended up with 1 here. And what I mean by this is when we said a plus b to the second, the first thing in our binomial here is a, and the second thing of our binomial here is b. And a is going to start with all of this n right here. That is, we start with a squared. And on my next term, what's happening is a is kind of giving off some of its power to the second term in this binomial, which is b in this case, over the length of the expression. So we say a starts with 2, which is our n, plus, now we say a to the first, b to the first, plus a to the 0, b to the second. And this is really apparent in this last expression here. We start with a having all of this cubed here, the n is 3. Then we say a squared b to the first, a to the first b squared, and then b cubed. So when I do an expansion like this, I can go ahead and tell you right now, what we're going to get is this. We're essentially going to get our first thing times our second thing here, where the first thing is getting all of this n. So we say to the fourth, and b is going to be to the 0. And we say plus. Now we get this thing here. We still say that this is a and a b, but now it's a to the third power, b to the first power, plus first thing, second thing, but now we have 2 and 2, plus first thing, second thing, but now we have 1 and 3, and then we say now plus first thing, second thing, and we have 0 and 4. Okay, so these a to the 0 and and in this case b to the 0, those equal 1, so we can discount those. But essentially, when you expand a binomial, what's happening is that all of this n value here is being distributed kind of evenly throughout. We say it starts in the front and then it goes to the other term through the progression of the terms. So the only other thing we have to kind of indicate here is this. So what would the coefficients of all these terms be? And actually, looking up here, we said, well, I'll kind of change colors here. We'll try to go for like a darker green rock in here, something like that. You'll notice that our coefficients up here, when n was 1, we said were 1 and 1. And when n was 2, we say they were 1, 2, 1. Okay, kind of hard to see there. And then we said when n is 3, we could pick up on the fact that we got 1, 3, 3, 1. And what I'm here to point out essentially is this. In general, what you get for a coefficient here, we say is n choose r. And we're going to look greatly in detail at combinations in the next video, but essentially for right now we say that it's this. And so what I'm going to tell you is this. All of these coefficients, we call them binomial coefficients, they can be found in something called Pascal's triangle. So I say let's sketch the first 3 rows of Pascal's triangle using combination notation. Well, what I want to do is start with just Pascal's triangle. And Pascal's triangle looks like this. We'd say it's 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and it's arranged like this also, 1, 4, 6, 4, 1. And as a matter of fact, what I want to do is I want to kind of split this up here. So what we could say is let's partition this into rows. I do want to indicate this. What I'm going to indicate off on the side is essentially that this is n equals 0, or we're going to call it row 0. So the interesting thing about Pascal's triangle is that it starts off at row 0. So we have the third row and the fourth row and so on and so forth, okay? But essentially, the nth row of this, what I'm doing to get the next row is I'm saying that I always have 1s on the outside, on these outsides parts right here. And then I'm just adding these together this way. We say the 1 and the 4 give me a 5. And I say, well, the 4 and the 6 give me a 10. And 6 and 4 give me a 10. And, you can see that there's some level of symmetry here. And this goes on indefinitely, as a matter of fact. We say this would be n is 5, row 5. So what I wanted to do is write this in combination notation. Now, the interesting fact is, when you write this out in combination notation, what you actually get is this. You get 0, choose 0. And I know, like I said, we're not having a conversation about combinations yet, but you get this. You get row 1, choose 0, and we get row 1, choose 1. And then we say this is going to be in row 2, we're choosing 0, row 2, choosing 1, row 2, choosing 2, and this actually kind of goes on indefinitely. So what I'm saying here is that 0 choose 0 is actually equal to 1, and 1 choose 0 is actually equal to this 1, and 1 choose 1 is this 1, and and 2 choose 1 right here is this 2 right here. Okay, so pointing those things out, what I can tell you is for right now, Pascal's triangle is actually a distribution of combinations. But to get our coefficients for our expressions here, what we can do is we can actually look at this triangle, because notice this. When we set up here, we said a plus b to the first power, where our n was 1. n is 1, okay? What we're saying is go look at this first row. Our coefficients are 1 and 1. So when we wrote this out, we said a to the first, b to the first. Okay, I get that because of the pattern of exponents. But we said that our coefficients, they were also 1 and 1, okay? So when we looked at this a plus b to the second power, okay, we knew we got a squared plus a to the first, b to the first, plus b squared, and now everything's been distributed, all of our exponents. But you notice that our coefficients are 1, 2, and 1, and when we go down here and look in this second row right here, I get 1, 2, and 1. And likewise, when I say n is 3, I go look at the third row here, I get 1, 3, 3, and 1. I notice that I get 1, 3, 3, and 1. So in general, what I'm going to tell you is this. We're actually going to pick up on the fact that you can use combinations to find it in general for some given term in a binomial expansion. But for right now, we say that we can just use Pascal's triangle that is easy to fill out and goes on forever and ever. You could always fill in another row just by summing those entries up in the top here. So we say 6 and 1, for example, here would be our 6th row. So that being said, we said, well, what about this expression a plus b to the fourth? I already know that it would say, well, a to the fourth, b to the 0, a to the third, b to the 1, a squared, b squared, a to the 1, b to the 3, and then a to the 0, b to the fourth. But what are these expressions here? Well, what I can do is I can tell you this. Because our n value is equal to 4. What we can do is we can just go look at the fourth row of Pascal's triangle, and what I see here is this. And I really want to point this out, so we'll switch over to like a lighter color here. How about a redder color? I get this 1, 4, 6, 4, and 1. So this would be 1, a to the fourth, b to the 0, 4 here, 6 here, 4 here, right here, 4 here, and 1. So if I were to clean this up a little bit, we say the binomial expansion without having to FOIL all this stuff out would just be 1a to the fourth, plus now I get 4a cubed, b to the first, and I won't even write b to the first. We say 6a squared b squared plus 4a to the first b cubed plus 1b to the fourth. And you can see how our powers, they start off with 4 all the way up on our first term here, and trading off as we go from left to right here, as well as you can see that the coefficients are reflected in Pascal's triangle. So in the next video, we'll look at how we can use this to our advantage a little bit more in a general way.